Okay, I think we have everything on the screen. Got to fix that thing. The problem that we're addressing here says that we have 500 sane and 500 demented people. And these people are immortal and they're non-reproducing. Not sure those two things are consistent. And 10% of the sane in any given year will become demented, while 20% of the demented will become sane. Now you see, if sanity is your priority, that's probably better than the reverse. You have more demented people tending to become, there's a higher probability that somebody who's demented will become sane than vice versa. Of course, if you got too many demented people, that 20% might exceed the number of sane people who are sane people, whatever the number is. I'm getting late in the day. You figure it out. Okay. Now, the problem's easily solved. Nobody had any problem with it. Nobody had any trouble with it. If 10% of your sane become demented, and you have 500 sane and 500 demented, then you're going to have 50 people in the sane category moving to the demented category, and 100 people from the demented category moving to the sane, because 20% of the demented will become sane. That means your number of sane will be reduced by this 50, but it'll be increased by this 100. So you have 500 minus 50 plus 100. You end up with 550 sane people. Okay, and in the demented, you're going to lose 100, but you're going to gain 50. Well, then you're going to have 500 minus 100 plus 50, or 450. It's very easy to understand, and we could take this another step, and we could continue doing this as long as we want to. There's a more efficient way, though, to do this calculation, and then an even more efficient way to represent it in terms of a matrix. So, if we have 500 sane and 500 demented, again, same situation, since 10% of our sane are going to become demented, we know that 90% of our sane are going to stay that way. So we know that in the next step, we're going to have 90% of our 500 in the sane category. We're also going to have 20% of these demented people in the sane category. So it's going to be 0.2 times this 500. Now, I probably made a bad choice using 500 for both, but we'll sort that out. So this is 90% of the 500 sane and 90% of the 500 demented, or 20% of the not 500 demented will be sane in the next iteration, or the next, I'm using 1 year as the time frame. So 1 year from now, that's what we'll have. If this is what we have now, this is what we're going to have then. And of course, you can do the arithmetic on this. That's 450, that's 100, it adds up to 550. The same as what we got here. So why do we go to the trouble? There are good reasons. Hopefully you'll see them. And then for the demented, 80% of our demented are going to stay demented. So we take 80% of this 500, and that's the demented who stay that way. And then we take 10% of our sane who become demented. So that's 10% of this 500. Okay, and that adds up. That's going to be 400. That's going to be 50. We're going to have 450, same as we had. So we can say, well, okay, whatever number of sane we have now, we have 0.9 times that number remaining sane, and 0.2 times our number of demented that are going to be sane, so that the number of sane becomes 0.9 times the number of sane plus 0.2 times the number of demented, number we previously had in the sane demented category. Similarly, whatever number of sane and demented we have 1 year from now, we're going to have 0.1 times that number of sane that have become demented, and 0.8 times that number of demented that have remained demented. Okay? So, a more efficient way of expressing this is to use matrices. Now, I've got the 0.9, 0.2 here. That corresponds to the 0.9 and 0.2 I have in this calculation. And let's see how. Okay? I've got a row for the calculation of the number of sane. I've got the row for the calculation of the number of demented. I've got what I call a column matrix or column vector. Here, I could call it either. If it has just one row or one column, then you can kind of call it a vector. If it's got more than one row and more than one column, you don't call it a vector. So that's a column vector or a column matrix. And in the column, I have the original number of sane and the original number of demented. Okay? Now, my rule is that when I can multiply a row of the matrix by a column of the column vector. Okay? So, I can multiply this row by this column. How do I multiply a row by a column? The rule is going to be the rule that works for these calculations. And that rule is I multiply the first number by the first number in the column. First number in the row by the first number in the column. Then I multiply the second number in the row by the second number in the column. Okay? First number times first number gives us 0.9 times 500. Second number times second number gives us 0.2 times 500. Now remember, this 500 is this one, this 500 is this one. Again, I probably made a bad choice using the same number. And then, what's that calculation going to correspond to? Well, the 0.9 times 500 is the 90% of the sane that remains sane, and the 0.2 times this 500 is 20% of the number of demented that become sane. Now, when I do that calculation, again, I get 450 and 100 adds up to 550, so that I add those two numbers to get this number here. So this column vector or column matrix is going to indicate, is going to represent the number of sane I have after the year and the number of demented. Now I take the second row and I multiply the first number in the second row by the 500 sane people. That represents the 10% of the sane that become demented, and that number is going to go into the second row of our column matrix. And then 0.8 times this 500 represents the 80% of the demented who stay that way, and that also goes into the second row of our column vector. And of course we add those two numbers up to get the 450 total demented people after one transition. And now we can do the same calculation, except applying it to the 550, 450. Okay? Now the 550, 450 population vector is the number of sane and demented after 1 year. 1 year after we have 500, 500, we have 550, 450. We do the same multiplication. Same rule. First number times first number, second number times second number. Gives us 0.9 times 550, 0.9 times 550, and 0.2 times 450 goes here, and we add them. And again, that represents the 90% of our 550 sane people that stay that way, and the 20% of our 450 demented people who become sane. Now, having used the first row to get this result, we put that result in the first row of our column matrix. Then the second row times the column matrix, the original column matrix, gives us 10% of our number of sane, that's the first number times the first number, and 80% of our number of demented, second number times second number. We add those and we get 585, 415. I think I did that kind of in my head, so check me on it. We could continue this. Okay, and there's even more that we could do with this idea of a matrix. Okay, very, very powerful idea. One of the two most powerful ideas maybe in mathematics, the other being the fundamental theorem of calculus. Okay, one note on notation. When I want to write a column vector, but I have to type it out, there's no good way to format that will actually work across various platforms, except platforms that you can't convert and can't manipulate. So I don't even try. And this is a pretty standard type notation. I write the column vector by writing it as a row between two brackets and put an apostrophe on it. Now, in set theory, that would mean the complement, but when you're dealing with matrices, that apostrophe just says put those numbers in a column when you write them. Don't put them in a row, put them in a column. Okay. Now, we're heading someplace with this idea of matrices, and it's very much related to stuff we've learned to do already with augmented matrices. And I'm going to make a couple of those connections. Well, I made a couple of those connections in class. I'm going to make them here, and hopefully you'll get some picture of where we might be headed with this. And of course, wherever we're headed there pretty quickly. Within a couple of weeks, you'll have this down very well.